What's happening here?
You're live. And here you go.
Perfect. And I can also draw with that one. Okay.
Draw.
So, good morning, everyone. I'm Markus Schädel and from Austria, so from Johannes Kepler University in Linz, which is the third largest city in Austria. Probably you don't know that, but maybe you've been to Vienna. So, well, I'm actually working at the Department of Computational Perception and the research field of music information retrieval. So, since maybe not all of you are familiar with this research field, I'd like to first start with a short introduction about what it is about. Then give you some examples of typical tasks my research is concerned with, and also give you some application scenarios and see why I think music information retrieval, music recommendation is important. And then I'd like to focus more on, well, a bit more technical aspects. Actually, I selected two research tasks which I think are, well, important for building music recommender systems and music retrieval systems. First one is how to measure similarity. And the second one is how to extract meaningful or hopefully meaningful features from different music-related representations. So you might wonder, what is music information retrieval about? And actually, it's kind of still well discussed in the community, in the research community, and looked into the literature and found different definitions for that. So quite early one, given by more or less, well, one of the founders of this research discipline, Professor Downey, said that MIR is a multidisciplinary research endeavor that strives to develop innovative content-based searching schemes, novel interfaces, and evolving network delivery mechanisms in an effort to make the world's vast store of music accessible to all. It's kind of a, you know, yeah, quite bombastic definition, but I highlighted here the important things, which is actually the multidisciplinary part. So, oh yeah, that works perfectly. Not familiar with this kind of things. The content-based searching schemes, you can see here. So content-based means basically, things extracted or encoded in the audio signal itself. But we'll talk about that a little bit later. Then kind of, well, maybe closer to what this course is about. So the database is a later definition given by Michel Fingerud. So actually, he defines MIR as actions, methods, and procedures for recovering stored data to provide information in music. So it means the data stored in a database and you somehow want to recover it. So the focus is on the databases in here. And a bit later on in my own PhD thesis, I defined MIR as follows. So MIR is concerned with the extraction, analysis, and usage of information about any kind of music entity. So, for instance, this could be an artist, a song, an album, a composer. So with any kind of music entity on any representation level. So typical representation levels are, of course, the audio signal, but also digital representation of the score. So probably you know about MIDI files, or also just the name of an artist or a web page about an artist that gives you additional information about them. So in general, music information retrieval is still a relatively young research discipline, especially compared with text-based information retrieval or database research. So it actually evolved in the 90s due to several reasons, which I'd like to summarize on the next slide. So as already mentioned in this early definition by Stephen Downey, it's MIR is extremely multidisciplinary. So if you go to the main conference, main scientific conference on music IR, which is the Izmir conference, the International Symposium on Music Information Retrieval Conferences, you'll meet a lot of different guys. So you meet computer scientists, of course, concerned with machine learning, databases as well, of course, but also human-computer interaction. You'll certainly meet musicologists, of course, who have a quite, well, sometimes a quite different point of view than we as computer scientists do. And then, of course, meet electrical engineers working on signal processing, or mathematicians as well, even sociologists, for instance, who analyze or who investigate how people organize music, or well, social aspects of group listening, for instance, listening in cars and so on, and how this relates to each other. Of course, psychologists are also involved. So, for instance, recently a hot research topic is music emotion recognition. So, investigating emotions that are caused when listening to music. So we see it's in general a multidisciplinary field, also in constant change, so highly dynamic. So recently we've seen a strong shift towards more listener-centric, user-centric methods, away from the pure mathematical computer scientists approaches, so to say. Well, and to give you a bit of an overview of the reasons why music information retrieval evolved as a research discipline, try to summarize this here. So, of course, we've seen technical advances during the 90s. So, increased computer power, of course, the invention of different compression techniques, like you all know, MP3, I guess, which was developed in the mid or late 90s. Also inexpensive data storage facilities, and all of these factors together led to the fact that people were able to store a lot of music on their hard drives, of course, which actually brought, well, some problems as well, how to access the music, for instance, or how to find suited music, so how to discover the hidden gems, so to say, in music collections. And of course, networking capabilities increased, broadband internet access, and so on, so which already led to the emergence of streaming services, which you all know, like Spotify. Who uses Spotify? Wondering. Oh, it's quite popular in Iceland too. Okay. Who knows Last.fm? Okay. Fewer people, but still. Okay, cool. Well, I'm trying to look at the recent developments, or the important current challenges are, well, that today we have high-speed internet access, of course. You're always on, you all have smartphones and so on. You're all using social media, I guess, at least most of you. So actually, we see a trend to, or a challenge to cope with the social interactions. Well, social recommendation, for instance, or personalization of music recommender systems. So these aspects become more important. And of course, also the streaming services, which gives you access to, well, tens of millions of music tracks. And for music information retrieval research, this actually means that we need to scale the approaches, because usually in academic research, you just use quite small collections, so not tens of millions of tracks, rather, well, a few thousands or at most tens of thousands. So scalability issues are important to address here. So what are typically tasks in music information retrieval? I try to summarize a few of them. So I'll talk about feature extraction and similarity measurements a bit later on. But maybe what all of you know is Shazam. Who knows Shazam? It's used it. Okay, so frequently when you talk to someone who is not familiar with music information retrieval, they'll say, yeah, that's all about Shazam, right? And this is related to audio fingerprinting, actually. So you kind of record a snippet of a song, and then will automatically compute some fingerprint and match this to a database, and then give you the metadata. Well, ideally, of course. So find the artist name, album name, song name, and then, of course, provide a link where you can purchase the respective album. Other tasks are, for instance, to automatically detect singing voice, or also particular instruments in a performance. So to identify different instruments in orchestra performance, or try to discriminate speech from music. So for instance, we had a project with a large broadcasting company, so TV company in Austria, which were interested in finding where in the program music occurs, actually. which is important for the royalties, of course, you have to pay. Another kind of task is structural analysis or also segmentation of the audio stream. So for instance, automatically identifying classical music, different motifs or segments that reoccur, or in pop or rock music, for instance, identify the chorus of a song, which is important for summarization, for instance. So you all know Last.fm or Amazon Music, you can usually preview a certain song, which actually means you can listen to usually 30 seconds of the song. And how to automatically define these 30 seconds to avoid, well, manual annotation, to manually find that. So to automatically find the kind of most important part or most representative part of a song, that's actually done in here with this analysis, in this analysis task. Another one is, for instance, what I like to call automatic karaoke identification, which actually means you, given a song, you automatically want to find the lyrics and align the lyrics to the lyrics given as a text. Okay, but that's pretty challenging, especially in death metal or in rap, as you can imagine. It works for some kinds of music, but in general, it's pretty hard. For choirs, it works to some extent. We don't have instruments, but it's a really challenging task. Then optical music recognition is kind of, well, if you know optical character recognition, then it's kind of similar. So actually you have a scanned, or typically a scanned score sheet, and you want to obtain a MIDI representation of that. So to a digitized representation of the score. And then MR is also concerned with several classification tasks. So for instance, given a big audio collection, you would like to automatically determine the genre of a new music piece. So whether it's rock or pop or Viking death metal or whatever. And of course, last one is, well, not the last one, but also a very important part is how to make accessible music collections to a larger audience. So how to develop intuitive user interfaces, browsing interfaces, make the interaction between the listener and the music collection as intuitive as possible. I'd like to give you a few examples for these interfaces later on. So, but let's first start with a typical well, scheme of an MIR system. So try to explain this one. It's again pretty database oriented. So actually what we start with always is a music entity. So by music entity, I mean something like a song, a track, an album, an artist, and so on. So typically these are individual tracks. And then the first thing we do, typically some kind of feature extraction indicated in here. So for instance, try to extract the melody line or the rhythmic structure of a piece. This will give you some features. And then you have kind of here the database part. So you want to come up with a simple representation of the features and store them in the database. So basically you want to index the pieces and then store the respective representations in the database. So that's kind of the first thing, kind of the feature extraction and analysis part. And then if you look here from the user side, actually if we start here with the query formulation, in all retrieval systems, you need to define, you need to give the system as input some kind of query. And actually we can distinguish three different approaches how to query such a music information retrieval system. The first one is actually the query by example strategy in here, where the query is similar to the music entity, which is taken here during the analysis step. So, for instance, this could also be just an audio file. Then we extract the features, you can see here, and then we match actually the extracted features with the database. So we try to identify the song or the track or the other item, and then actually fetch the true song, the true item, and finally present it to the user. So to visualize and, well, in the case of music, also to oralize the music pieces. So actually to play them to the user. Then we have the second querying approach, which is direct query, where in this case, the input is actually the feature itself. So this could be, for instance, already a tag or a melody line, for instance. I'll show you a few examples later on. And then we have the browsing, where usually you don't specify, or the user doesn't specify a real query, but actually the system selects the whole collection or a subset of the collection and presents it to the user in order to make it browsable, so to facilitate finding new interesting music. And then finally, we have the recommender systems, music recommender systems, which I'll talk about on Friday in the methodology course. I don't know who will attend that, or who of you has to attend that. No, not yet, of course. Oh yeah, that's a master one. Okay, so here for recommendation, a user profile is built. So actually, well, the system stores what you listen to, maybe also some clicking behavior and so on. And then it matches this user profiles with other ones. And again, through the identifiers, present you some hopefully interesting recommendations. So I draw a whole lot here, but I hope you get at least a very brief glimpse of how different music information retrieval systems work. So here again, yeah, I already told you that. So actually, and next I'd like to give you some examples of each of these modalities. So let's first start with browsing interfaces. Well, general motivation for this is, well, you know, music collection becoming larger and larger. You have access to tens of millions of music pieces at your fingertips, but still a lot of user interfaces stick to this kind of old searching scheme or browsing scheme where you can access the music by genre or artist or album name or track. So you usually need to know what you're looking for. So actually what we want to have to overcome this is some intelligent way to structure the music. And here, that's an early example developed by a colleague of us. So actually, he hacked an iPod, installed some Linux there, I think it was called Rockbox, and actually implemented on the device an audio feature extraction, so analysis of the content. And then he automatically organized the entire music collection in this colorful stripe in here, which allowed the user to browse using this Jocket island here. And he organized this so that consecutive music track sounds as similar as possible. So for instance, the user could then go to the yellow region in here where it found reggae music, for instance, or to the blue region where might be blues, and so on to the red region where there might be some heavy metal played in here. So, and there are several user interfaces have been developed and proposed in literature that always, or most of them, use some kind of clustering technique. So actually, based on these audio features, algorithms to try to automatically group the music collections or group the music items into some coherent sets, for instance, related to genre or to style. This is actually an example of another user interface. You see here the different colors indicate some kind of similar pieces of music, and then as overlay you have some tags in here. So you have happy music, romantic music, and so on. For instance, you also have an organization according to tempo, so fast and slow, and here along the x-axis you have different time periods. That's a nice example that was developed by colleagues of mine from Technical University of Vienna. So that's called the map of Mozart. So it actually uses a clustering algorithm, so a self-organizing map based, which was trained on rhythm patterns. So actually this algorithm organizes the entire works of music based on these features and visualize this as a kind of a heat map-like visualization using Mozart's head as borders, so to say. And then you could, like here, for instance, you can draw a line you can draw in Mozart's head to create a playlist, so to say. Sorry? Well, okay, but I can, yeah. I think you can imagine. I mean, you have the red line here as well. You can draw arbitrary lines in Mozart's head. That's another example that uses a similar techniques, also clustering, self-organizing map in that case. That's a system developed by a colleague and by myself. Actually also extracts first some features from music collection and then visualizes them in the landscape, which you can access, so like in the computer game, so fly through that. Another example here by Masataka Goto, so it's a pretty famous professor and researcher in MIR. It's well, pretty Japanese. So it's also well, a game-like interface where you have different, well, kind of tabs here, and the lever here we can define the speed which the individual songs in here. So each of them represent songs pop out. And for instance, the red one would represent rock, the blue one classic, and so on. And then the user can just drag and drop them to a region in here, and also create playlists by sticking together the different tracks. And was implemented in a way that if the music tracks are close, it's quite easy to stick them together. And if they're very different, so from different genres, they have repelling forces. So you have to really push them to make them stick together. Well, for the sake of time, I'm gonna skip that. So we have a lot of other user interfaces. That's Songroom, that's a quite recent one, also developed by some guys from Japan. It's very colorful, of course. You have again some feature extraction step and then clustering technique in order to create this kind of planet-like or galaxy-like interface. And then you can zoom in and, for instance, select a particular piece, and it would then link you to different YouTube videos or some Japanese version of YouTube, Niki Doga, I think it's called, and you can then access different versions and also browse by different genres. So that much for the browsing. The next querying strategy I'd like to tell you more about is the direct querying. So remember, this actually means that the input is actually the features themselves, which are extracted or which are stored for the individual tracks, and you use as input the same representation as the analysis step. And for instance, a typical example here, I cannot, do I have internet in here as well? Oh yeah, here, so Musicpedia. I have here the example of Theme Finder, but there is a newer version called Musicpedia. And for instance, typical example is this contour search in here, which actually would allow you to search for a melody where the features are, of course, the individual notes played. And using this, what's called parse code, you can define, for instance, a sequence of notes, not as the notes themselves, but as changes in the pitch interval. So for instance, you could search for a melody saying you want to start with a note, the next one should be higher, the next one should again be higher, then it should stay the same, which is R for repeat, and then it should maybe go down. You can enter something like URD in here, and then click search. And then, well, as you say here, it will give you some examples. You have the contour here as well, and you see first goes up, stays the same, then goes down. I think I'm not allowed to play you the music in here due to some technical or legal reasons, but you can try it out. It's just musicpedia.org if you're interested in that. That's a pretty nice system. Another example for this direct search, if you use semantic tags, so for instance, Last.fm here, most of you know them, you can of course directly use this semantic tag as queries. So for instance, just say aggressive in here and we'll give you a lot of extreme and aggressive female fronted music, for instance. Of these things. And the final modality is this query by example I already mentioned, and well, already told you about Shazam, most of you know, so I don't have to repeat that. There is also a special kind of interfaces, techniques called query by humming, where the user, instead of recording an audio clip, hums to the microphone. So, for instance, hums a melody, and the system then tries to identify the respective song. So, of course, the performance here depends on the singing qualities of the users to some extent. So, it sometimes works very well, but especially for larger music collections, the performance might be poor. So a pretty famous example, or a well frequently used app, is the SoundHound. Anyone knows that? Oh, quite a lot. Okay. So, well, you probably recognize that it works pretty well for popular music and not so well for music that is, well, not so frequently listened to, I guess. And the reason is that they store all the hummed melodies in the database. And of course, like, I don't know, a hit by Lady Gaga or Madonna will lead to many more entries in the database. So it's easier to find a match than for a rather unknown band. So, and finally, after these examples, I'd like to give you a very brief introduction about two things that are very important, or two tasks that are very important in music information retrieval. The first is to measure similarity. So, you know, if you have a query, then for any MIR system, or in general for any retrieval system, you have to somehow quantify the similarity between the query and the music items you have in the database. And this, of course, enables a wide variety of applications. So you can query the databases, as I just mentioned. You can build recommender systems where you, well, in a content-based case, compute similarities between the individual songs and then recommend music that is similar to the music the system knows to be liked by the listener. Or in case of user-based systems, it's important to compute similarities between the individual users. But more about that on Friday, as said. You might even want to participate if you want to know more about that. And finally, automatic playlist generation. I already gave you this example of the what we call intelligent iPod. And also for browsing interfaces, of course. So the clustering technique will only find clusters when we have some meaningful features and tries to identify similar sounding music pieces and group them together, well, here on this landscape interface, for instance. Well, in order to be able to compute some kind of similarity between the representations of music items, we need some kind of computational features that represent at least some aspects of the music under consideration. And there are different ways to define this, and there are many different facets or aspects that influence how we perceive music and also influence how we perceive similarity between music. So, for instance, if I if I play you two pieces of music and I might ask, I don't know, you, for instance, whether they are similar, say, yeah, they're very similar because the lyrics are similar. If I ask, well, your neighbor, for instance, they will say, yeah, the songs are very dissimilar because the melody is completely different and so on. So this is also kind of a very subjective thing. So nevertheless, we've tried to identify different categories of what influences music perception. And the first one are aspects of features that are encoded in the audio signal and can be extracted from that. So for instance, the melody line, as I just mentioned and shown in this example of Musicpedia or also Theme Finder, or the timbre, the rhythm, the instrumentation, and so on. So all of these things. And there is a whole lot of aspects that are not encoded in the signal itself, but are nevertheless important. So for instance, the background of a singer, the meaning of a song lyrics, is it a protest song, a love song, a war song, maybe, and so on. And then finally, of course, also user-specific aspects influence how we perceive music. So there are general user properties. So for instance, the musical expertise or knowledge of a listener. So someone who has been playing the piano for 10 years might have a very different perception of a music piece than someone who has not. So with the user properties, more or less more static things, include demographics, musical knowledge, and so on. And then we have the current context of the user that also has an influence. So for instance, the current mood a listener is in, the social context, is the user together with friends or family, or listening to music during workout, for instance. So all of these factors influence the perception of the music and of a similarity between music pieces. So, and very briefly, to give you two examples of the main kind of categories of feature extractors, which are the music content in here and the music context. I selected, well, two examples how to compute or how to extract these features from the audio signal. So just to give you an overview about how such techniques work. So we start with some analog continuous audio signal. And the first thing we do is to sample it. So for instance, to create a CD, we take 44,000 individual measurements, so samples per second, which actually gives you the waveform, usually also called pulse code modulation. So you probably know that if you open any audio editor and open some respective file, then this will give you the waveform, actually. So actually, these are measurements of the amplitude over time. And of course, you also have to quantize it. So actually, you have a limited number of bits that you can use to represent each of these samples, so each of these measurements. And then you have to aggregate them, which is actually called framing typically. So this means that you create individual chunks. So you put together consecutive samples. So for instance, 512 samples could form a frame, and then you compute some kind of features for each of the frames. So this will already give you what's called time domain features, because it's computed directly in this time amplitude representation of the music. And then kind of the second category of features, the so-called frequency domain features. So I don't know who heard about fast Fourier transform. Yeah, only one. Okay, so I won't go into detail about that, but in general, these are maybe you will hear about that in the remainder of your studies. In general, the basic idea is that you transform this time domain representation, so you have amplitude over time, to the frequency domain representation, which actually means it gives you an indication about the presence of certain frequencies. So are there higher frequencies in the signal? Are there lower frequencies in the signal? And we'll tell you about the energy in these individual frequency bands. So of course, for trance or dance music, there will be a large amount of energy concentrated in the lower frequency bands. And that's something that the result of the FFT will tell you. Then you finally aggregate this individual information, because you have you compute this kind of features for short segments. So for instance, for a few milliseconds or up to 6 seconds, in the case of frequency domain features. So you have to somehow aggregate these individual values or vectors in order to be able to compute similarity based on a fixed number of dimensions which you represent the audio piece. So this will actually give you some scalar or a vector or even matrix representation. And if you computed this for the entire music collection, then you can apply some similarity measure in order to assess how similar the music pieces are in your entire collection. Or you can also compute this, of course, between the query and the individual music items. So this really depends on the task. If you want to automatically create a playlist, for instance, like in this user interface I've shown you, then you have to compute similarities between the individual items. If you have a query and you want to match the query with the database, then you have to compute the similarity between the query and the items in the database, of course. So, and these content-based features can be categorized also according to different factors. So, for instance, the level of abstraction. There's something called low-level features and high-level features. The low-level features are the ones closest to the audio signal and are typically only to be understood by, well, computer scientists or electrical engineers, for instance. So this might be the direct result of the FFT representation. On the other hand, you have the higher level features, which are semantically meaningful to each of us, usually. So this could be some mood or how aggressive a piece is, or a style or a genre indication of an individual piece. I'm gonna skip that. Of course, there are different features that describe different aspects. So for instance, you can describe the timbre, relates to instrumentation. You can extract rhythm profiles or rhythm patterns that gives you information about beats that occur or that reoccur at a certain periodicity and certain frequencies. And of course, you can also extract individual pitches to extract the melody, or to create something called pitch class profiles that will actually give you for each of the notes in an octave the amount of notes played summarized over the entire piece. Well, I already said, or basically time domain features and frequency domain features. Well, and finally, in the last 5 minutes, I'd like to tell a little bit more about this music context-based features. There are a lot of different data sources from which you can extract information that is not encoded directly in the audio signal, but that is nevertheless important to our human music perception. So commonly these sources are web-based, well, in a wider sense, so social media is used as well. So for instance, can be web pages retrieved via search engines, can be microblogs. So I did myself a lot of studies using microblogs to extract musically relevant features. Can be extracted from product reviews, like from Amazon album reviews or opinions. Can be semantic tags. So I already showed you this example of Last.fm. Lyrics are frequently used and analyzed using some text processing techniques to identify different groups of lyrics, as already said. Is it a love song? Is it a war song? And so on. And of course, Wikipedia is also very frequently used. So don't want to go much into detail about all of these text processing techniques, but in general, as you can already see, most of these sources are text-based. And since text-based are and natural language processing is a quite well-established research field, the good thing in here is that you can draw from a large variety of different techniques that have been developed in text-based information retrieval. So finally, I'd like to give you one example of how such a context-based feature extractor works. And this is actually the typical pipeline of early versions which are still used of such a web-based feature extractor. So actually, it starts quite simple. You just use, for instance, the name of an artist or the name of an album which you want to model, and you query a search engine like Google, Bing, well, you name it. So you query for the artist name and you add an additional keyword to steer the search towards this music-related things. Because if you otherwise search for bands like Hole or Bush or so, for instance, or Madonna, this will very likely give you unrelated web pages. Then the next thing is, so you have these individual artists depicted in here by the colored hats. So you go, for instance, to Google, you download the web pages, usually not all of them, of course, but just the top 50 or top 100 results, which gives you, well, a variety of web pages that are hopefully related to the artist under investigation. Then you concatenate all of them, and then you apply different information retrieval techniques. So basically what you do is you, for instance, or you try to identify words that are discriminative for the artist under consideration. And there are a lot of different ways how to do this. So very frequently used technique is so-called TF-IDF, so term frequency inverse document frequency, which actually gives you a weight for each of the term, how important this term is in the context of a certain artist. And it will actually penalize terms that are important for all of the artists, terms like music or rock or band, get a lower score than more specific terms like Viking death metal or something like that, which is discriminative for a certain band. Well, and actually what you end up with is some kind of features in here, which you can then use in order to compute similarity again, or also for classification. So if you present to the system an unknown artist in here, you can do the same. You can go to Google, so adding the term music, downloading the web pages, and then match them with other artists which are already in the database, and for which you know the genre, for instance, and then you select the ones that are closest to your new artist and predict the respective genre. That's actually what is called the k-nearest neighbor classifier. Was already heard this term? Yes, classification? No, not yet. Okay, but that's the rough idea of that. So you can use it to create a playlist, for instance, to find similar artists, but also to automatically classify a new artist according to genre or to some other things. So I think we're running out of time, so maybe I'm gonna skip that and wrap up. So there are, of course, other techniques that can be used to compute similarity. So quite simple approach, maybe just let me say not that much for that, is so-called co-occurrence analysis, which actually means that you download again a corpus of web pages, for instance, for each of the artists, and then you investigate for a given artist how frequently any of the other artists in the collection occur in the context of the web pages. And the basic assumption behind this is that an artist occurs more frequently on the web page of another artist if these artists are more similar. And then you can again compute so this co-occurrence matrix. So this would, for instance, give you this information that you found 100 web pages for artists. The first one, Alice Cooper, and on 3 out of these 100, B.B. King also occurs. Okay, if you focus on B.B. King, then on 0 of the B.B. King web pages, Alice Cooper will occur. So actually this kind of gives you an asymmetric matrix, so you have to make it symmetric in order to define a similarity measure again. So that's another method that is sometimes used. So to wrap up, hopefully shown you that MR is a quite multidisciplinary research field that's becoming more and more important. So especially look at the evolution of music recommender systems, for instance, and music identification services. There are content and context-based features which are important in order to compute similarity and can be used for browsing, for direct querying, for query by example, and also to build music recommender systems. And one of the most important, at least in my opinion, challenges is to create systems that are really aware of the listener and consider the listener in a holistic way. So actually not only like current collaborative filtering recommender, only consider what the user listened to, but also consider the context as indicated on this diamond-like structure. So, and finally, some advertisement, because I'm really proud that our book is out. So I've been working on that since, well, 4 years, postponing the release by 2 years in total. So if you're interested in this, then there's this book by my colleague Peter Gnees and myself called Music Similarity and Retrieval, Introduction to Audio and Web-Based Strategies. If you don't want to buy it, or if you don't have the money, you can download a free version. Well, it's not the whole book, but it's kind of a summary of the book, so to say. So sort of music similarity and recommendations from context data. So it's omitting the audio-based part, where I'm admittedly not the expert on, but focuses on the web-based music context-based parts. So that's freely available. If you want to have a look, then feel free to download it from that URL. So thank you very much. If you have any questions, don't hesitate to ask. Thank you. Oh, okay. But this.
I have one.
Sure.
Are there any, where is deep neural networks and neural networks?
everywhere recently. Well, I just returned from the ISME conference, which took place in New York 2 weeks ago. And as in many research domains, deep neural networks and deep learning is becoming more and more important, of course. Yeah, sure. I mean, it works for some tasks. A colleague of mine actually used it for music onset detection. It's actually where a note starts. And he used as input just a spectrogram of the piece